Hi and welcome. I'm Corey Kell, and this week's block of instruction for the weekly video update 1.1 is we're talking about using the sun to determine Earth's true surface shape. Welcome again. We'll talk a little bit about understanding the use of the sun in the equatorial plane and the tropics, why it's the sun is the answer. History's key players. We'll talk a little bit more about history's key players and what it really meant. What is vertical angle and why it's the answer, the two sciences that use it. The sun at 90 degrees and what it really means. And then we'll get into a little bit of geometry and triangulation, why it really works, and the sciences that use that methodology. Let's talk about the definition of the equatorial plane. What is it? Dictionary.com definition: the plane passing through the equator of the Earth or another celestial body. And from Science Direct, their definition: the equatorial plane intersects the celestial sphere in the celestial equator and the polar axis in the celestial poles. The Earth motion around the sun is then pictured by the apparent motion of the sun in the ecliptic, which is tilted at 23.45 degrees with respect to the celestial equator. The angle between the line joining the centers of the sun and the Earth and its projection in the equatorial plane is called the solar declination angle. We talk a little bit about that in our book. And the angle is 0 at the vernal equinox, 2021 March, and autumnal, which is the spring equinox, and autumnal fall equinox, which is 22-23 September positions. So quite a definition. Let's get a kind of a picture. This is what they're talking about in the heliocentric globe model. You'll see here the equatorial plane is laid out, kind of that square as it's laying flat. At the vernal equinox is that's sun position to Earth, where the sun is at the equator. If you were at the equator, it would be, you would look straight up. There would be no tilt at that time. It would be 90 degrees straight up if you were at the equator. And of course, the sun, as it gets into the globe model tilts as it gets into the summer seasons. The globe actually tilts towards the sun, keeping that sun or maintaining that sun at 90 degrees, which again is which leads into a fundamental flaw for that model. We'll take a little bit more in-depth look at that. Let's take a look at that. What sun position at 90 degrees? What does that mean in simple terms? Here we see a diagram. We have the globe model, and this puts the sun always at 90 degrees to Earth in the equatorial plane and tropics. So whether it's during the vernal the equinoxes or in the summer sun season, that sun is always 90 degrees. And if the sun, as the Earth tilts, that going towards the southern hemisphere, as the sun, as you see it moves to the Tropic of Capricorn, that begins the spring and summer sun season in the southern hemisphere. It's that band, that belt that goes around the Earth, as you can see there by the diagram. So the globe model then tilts towards the sun, and we'll show you a diagram of that in the following diagrams. But here you can see that belt. That belt is the belt where the sun's operating range is for both models, actually the flat Earth and the globe model. So in the southern hemisphere we get the summer, as that sun is located at the Tropic of Capricorn. And as it returns back, you get fall, going into winter in the south, and then spring and summer in the northern hemisphere. And again, that globe tilts back towards the sun during the summer, maintaining that sun at 90 degrees. And again, this becomes a huge problem, as we'll talk a little bit more about that. The sun and the lollipop. It's kind of like a lollipop. The sun is like a lollipop on a stick, and maintaining its 90 degrees. And here we have three globe images showing you what I'm talking about. For the globe model on this side, here we have the sun up in the summer sun season. It's 90 degrees as the globe tilts on its orbit around the sun. And then when we're at the equator, we got the equinox. You don't have any tilt. It's at 0. There's no declination. There's a 0 degree declination. And then in the summer, in the south, you get that tilt towards the summer sun in the south. Again, that globe tilting, and to maintain that 90 degrees, or that lollipop on the stick. On the globe model, it's just on the side. So it looks a little bit different. On the flat Earth model, as you see over here, it's different where the lollipop on a stick orbits over the flat Earth in those rings. Same concept, except there's no tilt. The sun just orbits over the top of the flat Earth in a clockwise manner. So same concept. And here we just, this diagram just shows a little bit more about the seasons and during the equinox, the sun's position. Again, always maintaining the 90-degree position. So the sun is always, so if you were up in the north and during the summer, during the solstice on the Tropic of Cancer, that sun would be directly overhead if you were in the right position along the Tropic of Cancer when the sun passes over the top of you. Same thing if you were at the equator during the equinox or in the southern hemisphere and the Tropic of Capricorn and the Earth tilted, keeping that sun at 90 degrees, and you're on the Tropic of Capricorn during the solstice down in the southern hemisphere. Same thing. Let's talk a little bit, going back into history, when we talk about the shape of the Earth. And really, we talk about equations versus reality and experimentation. And some of the key players, of course, the Copernican globe model was formulated by or brought in by Nicholas Copernicus, who I think knew there was an issue with vertical angle. I think that's why he didn't release his model while he was alive. I think he knew there were problems with the sun being out of position in the daytime sky. And we'll get into a little bit more about that in a little bit later on. But he basically, the foundational work for heliocentrism. Samuel Rowbotham Bedford-Level experiment, which kind of was an experiment to test Earth's surface shape, one of the earlier models. Test done in England. And then really the key experiment that science tried to provide proof of that the globe was, or the Earth was moving. The Michelson-Morley 1887 experiment, which failed. It failed to show the Earth was moving. And then they said, well, there was an issue with it, or they had something they didn't calculate, but they tried to make up an excuse for it. And it turned out very badly for science. As a matter of fact, it turned out so badly for science they had to bring in Albert Einstein, who then had to say, hey, we need an equation, because what we're seeing, what we're experiencing in reality, we need an equation. So Einstein's theory of relativity was the answer to that. And science, but again, science came back. George Sagnac in 1914 conducts the same experiment as the Michelson-Morley, gets the same result. So again, a failure in Einstein's theory of relativity, and then you have the advent of science fiction. So if you can't get that model to work one way, mix it in with a little science fiction to help sell that model, and that's what occurred back in the early 1900s, 1926, when you have the advent of science fiction. Science used science fiction to help sell that model. The person that saw what was going on, Nikola Tesla, probably one of the smartest guys to walk the face of the earth. He made the quote, and this was directed at the heliocentrists and Einstein. He said, today's scientists have substituted mathematics for experiments, and they wander off through equation after equation and eventually build a structure which has no relationship to reality. And he was talking about the heliocentric model. Specifically, he was talking about the sky. They made the sky mathematics. The sky was never meant to be mathematics. It's meant for signs and seasons, ambience and beauty, as it's told and is created by, in the Bible, the heavens and the firmament over us. Again, Nikola Tesla called out the heliocentrists. He knew what was going on. What Copernicus would add to verify for the globe model, directional azimuths, in other words, the sun being at a certain direction during the daytime, and that kind of works. It works out if we look at it from the Earth. However, the vertical angle, the height of the luminary, the sun in the sky, that fails. The sun is too high in our daytime sky, especially during the summer. What we should actually be seeing, the summer sun height happens to us up here in the north during the winter. And that's about the height of the sun we should see in the summer. And then even in the winter it should be a little bit lower. So the sun's out of position. Complete orbital mechanics, direction and height. So you have to have a combination of not only directional azimuth, but you have to have position and height in the sky, and that fails as well because your sun's out of position. And the sun's position in the sky seasonally, again, this fails because, again, the summer sun is just too high. It's out of position. And again, I think that's the intent of the Creator. It's one of the fundamental building blocks why the Creator put the sun high in the sky, for us to identify that. What works against a heliocentric model? Distance. Once you exceed that limit, the farther you go out for this model, the farther you go out for this model, the farther you go off the line of parallel. And you see the lines of parallel 1 and 2. Line of 1 is the sun at 90 degrees. Line 2 is measured from the OS. So if you're doing something like the 45-degree sector test at 3 hours, if you're 45-degree angle to that object or the sun, you can't exceed 45 degrees. It's very simple. Separation between the lines cannot exceed the sun's size, and that does. And once you get up in the 46, 47, 48, 49, 50 degree range. The equatorial plane in the tropics, this puts the sun at 90 degrees within the area or the belt surrounding the globe model. The globe tilts to maintain this 90 degree sun. Because of this, it becomes very short conversation as to the sun's height and the model's limit with regards to measured vertical angle from the OS. You got to know the limit, knowing the model's limit. The globe model spin because the sun is out of position in our daytime sky. Timing is associated with spin. This also tells us that the orbital rotation for this model doesn't work. This means the sun is orbiting over a stationary flat Earth. Again, these are all the things that work against the heliocentric model. Stuff that they need that model to work. It actually works against it. The rings of latitude, and really when we talk about surface angle is determined by distance on the globe using the latitude and longitude, those squares on the globe model as here we're showing. I just highlighted the 2 rings there in red. And these rings of latitude, again, when we're using the globe model, surface angle and distance equate to each other. So the rings are the geometric rings or the circles on the globe. And that works against that model. And here I show you an example of this, measuring distance and surface angle on the globe using latitude and longitude. A lot of people say, well, you're using the wrong map, but in digital mapping, it gives you the exact latitude and longitude position of the sun determined by the azimuth from the OS. So if we add a measured azimuth to the sun at this, say that this is the Tropic of Cancer of the sun, we can then determine its distance based on its azimuth and then the location, the latitude and longitude, which is given on digital mapping such as Google Earth and Google Earth Pro. And here this this globe model has a scale of each one of these latitude and longitude squares is 10 degrees. So there are a total of 36 boxes in each ring, which creates a circle, a circumference of 360 degrees. So here we have 10, 20, 30, 40, 50, and then halfway through is 55 or 55 degrees. That's the surface angle the observer is at to the sun at the measured time of vertical angle, testing the vertical angle or measuring the sun's height. And that's just an example. Again, very simple. It's nothing really hard, but it's not taught in traditional education. So again, we'll talk a little bit more about the 2 sciences that do use it. And what is the fundamental flaw in the globe model? What's the equatorial plane, the sun in the tropics, the sun's operating range, and the globe's tilt? These all work against that model. And once you have that sun that's at 90 degrees, if that sun is directly above in the equatorial plane on the equinox, that sun is directly above the equator on the Earth. You can't get around, you can't escape it. In other words, that globe model tilts. It's almost like a magnet, keeping it, that model, keeping it at 90 degrees in the tilt. That is the fundamental flaw in the globe model, and I think Copernicus knew that. That was a huge issue. Because it leads into triangulation and the actual distance and size of the sun. Simple use of, some people don't believe that 90 degree, I had a guy that said he didn't believe that existed, but that's like saying a stop sign isn't 90 degrees directly above the Earth. When we use a post, we simply remove that post and that stop sign, again, still 90 degrees above the surface or above the ground, above the Earth. And that would be the same if you saw a bird flying over your head or an airplane flying over your head. Same thing. It's 90 degrees directly above you. And we can do the same thing for the sun, because the sun is at 90 degrees at the equinox and during the summer sun season. So we can get a clean angle, or a triangled survey shown here on the right. Use of triangulation, its extensive use in military science and civil engineering. Vertical angle can be attained. In other words, we can get a clean, very clean angle because the sun is at 90 degrees, and then it becomes part of that surveyed triangle. And once you have a surveyed triangle, that sun is part of that triangle. It's within your visual perspective. You can't escape it. And again, this is what I'm talking about, the surveyed triangle. If you, the sun we see in our daytime sky is very, very close. The hypotenuse, or the vertical angle, you measure the height to the sun, and then the line, or the line of the survey, or the sun plot, determined by azimuth going to the sun's 90-degree position on Earth. So if you're at, let's say, in the northern hemisphere on the solstice, you'd be at the Tropic of Capricorn. You'd get an azimuth to that location for like the 45-degree sector test or long distance testing. And that is the sun's 90-degree position to Earth. That is part of the surveyed triangle. And that's, again, that's a major, major problem for the globe model. It's a huge fault. And again, why I believe that Copernicus understood that, and that was a huge problem. Triangulation and how it works within our visual perspective. Example, note the lines intersect the sun, being part of the triangle within that triangle that is surveyed. So it's part of the triangle. And actually the physical sun that we see, or the sun that we see in our daytime sky, is part of the surveyed triangle. If it was outside our visual perspective, we wouldn't be able to see that sun, or we wouldn't be able to see that object we're trying to obtain a vertical angle. It's beyond our vision, or outside our visual perspective, and it's not part of the surveyed triangle. So this could be the projection. Many of us believe that the sun is actually projected from a projection device into our atmosphere, and that could be the projection device at an angle where we can't physically see it. But again, that sun that we see in the daytime sky, we can get a vertical angle on because it's part of it's within our visual perspective. Very simple, and triangulation works. Vertical angle is the measured angle of the height to an object. And it's simple, very simple definition. Measuring vertical angle to the sun, measuring the sun's height. Again, when we sight in on the sun, we go center mass, or line of sight. When we're actually measuring it, we're actually measuring half sun when we look at taking the size into consideration when we're doing vertical angle testing. The limit is the edge of the sun, or the half sun size. So I think it's right around 440,000 miles. The sun size being right around over 900,000, somewhere right around there. So again, and that's the heliocentric globe model. Again, vertical angle, measuring that angle to the sun, that's what it looks like. The two scientists who use vertical angle in their real-world applications, the two modern-day scientists that mostly use vertical angle in their applications: military science, gunnery, live fire, safety, artillery, small arms, combat engineers, all use vertical angle. We'll give you an example of that. Civil engineering, the other major science: bridges, road engineering, building structures, and railroads. Note astrophysics is not listed because, well, they're using equations and size ratios. And they had to go outside and do equations to make their model work. But it's not what we actually physically experience and what we actually physically see. And again, using basic geometry and testing. The military science live fire safety box is an example of military science. Vertical angle is used, and here we have the artillery piece or howitzer firing into a safety box, which is located in the impactor, and you have a near limit, which is the limit closest to the artillery piece, a far limit, which is the farthest away, and then the left limit and right limit. And that must know vertical angle is calculated based on its distance to the impact area, or the target range, on the azimuth of fire, and then that's computed into that determines the charge, and the weight of the projectile is also calculated into it. So there's a lot of stuff that goes into this, along with vertical angle. These are lines of parallel, designated limits, near, far, left, and right. Again, and when artillery pieces fire, they can't see where they're firing in for indirect fire. and they have to have an FO which spots that round or sees it land safely into the impact area. Again, military science use, heavy use of vertical angle. The other science, civil engineering, for on this one, bridges, the effect of vertical angle bridge height example. Semis are 13.6. We have two examples. One bridge underneath or underpass is at 12 feet 4 inches high. This would be too low for that semi. That semi would hit the bottom of the underpass of that bridge. Or at, if you here see this example on the right, a bridge at underpass at 13.6. This semi could easily could pass through without any damage to the bridge or the semi. Again, just a simple example, vertical angle, and its real world applications in both sciences. The Gleason's flat earth map. I believe this is a major breadcrumb left behind us to help us determine what we actually live on and where we actually live. This is the flat earth map, the 1892 Gleason's map. Some people I've seen, some people said, well, this is actually a globe. No, it's not actually a globe model. It's laid out because of your Antarctica is the white ring around it. Each one of these pieces of the pie here that's broken down are 24 sections at 15 degrees for 360 degrees, and each one is 1 hour. So there are 24 of them for 24 hours, and this is the timing ring which goes around the outside, and this was created by some folks up in England here. You have solar noon at that position in England. The most important part, a lot of people get lost in the sauce on the diagram, but the most important part of the map is up towards the top, and that gives us linear alignment. And then if we were, this can be used to help teach why at 45 degrees to the sun on the globe model, if you're 45 degrees, that sun has to be 45 degrees in the sky. And this is an excellent training tool for that because the observer is oriented at 45 degrees for both westerly and easterly readings. So it's westerly and easterly reading 3 hours after solar noon and 3 hours prior to solar noon. An excellent example. And then also it talks about the solstices, and it gives us an illumination here on the bottom. So there's a lot of information on the Gleason's flat earth map. It's an excellent document, and I believe a major breadcrumb that was left behind. There's no known copyright to it as well, so that's another factor. Again, I talked about solar noon manual alignment. You have to set that edge. That's setting the edge once you get alignment, linear alignment. This is a side view, so you're on line with the sun. Not the sun being directly overhead, but your linear alignment. We use a Mark's device and a compass on magnetic north to achieve that. And then once you get that alignment, then you can start your time and do your testing. That sets the geometric edge, and you need to do that. That needs to occur for accurate readings. Defining the limit, you have to know the limit. I had a discussion with a professor of science in California, and he couldn't identify the limit for the model, for the globe model. So if you're at 3 hours or 45 degrees of the sun, what's the limit? Couldn't identify it. It's because they haven't learned it. They're not taught it. So if you're not taught it, it's going to be totally foreign to you. And again, that got him into trouble because he couldn't identify the limit. He didn't know the limit for his model. And if you're 45 degrees, such as shown on this slide, that means your sun has to be a vertical angle height of 45 degrees in the sky. Now some people will say, well, yeah, but this 45 degree position just goes straight up. No, that's not how it works, and we'll show you what I mean in the next slide. We'll take a look at the next slide. Because once you go up that scale, when you're measuring vertical angle, if you kept going up on the line, no, you're going from 45 to 46, and this is all over the limit for the globe model in a 45 degree sector test. So you have to know that limit, and then once that sun has to be in that position. If you're viewing a sun that's up 50 degrees in the sky for the 45 degree sector test, you're viewing it from a flat surface, not a sphere or a curved surface. And that's just knowing the limit for that test. Very simple test, line of measure, acquiring it. And as you can see, the little image on the left, there's a A digital protractor aims center mass of the sun, and you have an angle above the sun, an angle below the sun, and an angle right at the sun. So again, that's what it looks like, vertical angle testing. This concludes this week's presentation of video 1.1 using the sun. I hope you've enjoyed, I hope you've learned something from this presentation. I'll continue to do them and update weekly videos. I'm Corey Kell. Thanks for watching.